Okay, I think it's time to begin. Our next speaker is Sachchidanand Prasad, and he will speak on Morse-Bott flows and cut locus of submanifolds.
Okay, thank you. I would like to thank the organizer. Okay, so I'll be talking like as the geometric aspects of the cut locus, where I'll be discussing how the cut locus is related with the Morse-Bott flows, and lastly I'll be talking about the topological aspects of the cut locus, where I'll be discussing what is the relation between the cut locus and the Thom space. So let's begin with the definition of Morse-Bott function. So if M is a Riemannian manifold and N is any smooth submanifold of M, then we say that it is a non-degenerate critical submanifold of a real valued function f if this N is a subset of critical points of f, and for any point P, the Hessian is non-degenerate in the direction normal to N at P. So by this, I mean that if I take any vector V in TP and POP, then I can find a W in TP and POP such that the Hessian is non-zero. So a Morse-Bott function, this function is said to be Morse-Bott if the connected components of the critical F are non-degenerate critical submanifolds. So just for recalling, so all the Morse functions will be Morse-Bott functions. So now we will define the second part, which is like the cut locus. So before going to the definition of cut locus of submanifold, we need distance minimal geodesic from a submanifold. So if M is a Riemannian manifold and N is a submanifold of M, then a geodesic gamma is called a distance minimal geodesic joining the submanifold to point P. If I can find a point in N such that this gamma is a minimal geodesic joining Q to P, and by minimal here I mean that the distance between these 2 points P and Q is same as the length of the geodesic joining P to Q. And of course, the length of gamma should be equals to the distance from P to N. And we will call this type of geodesic as N geodesic. So now coming to the definition of cut locus. So M is a Riemannian manifold and N be any non-empty subset of M. So the definition is makes sense for any subset of M. And we denote the cut locus of N by CUN, and it consists of the point Q such that if I can find an N geodesic joining the submanifold N to point Q such that if I extend that geodesic beyond Q, then it is no longer distance minimal. For example, consider the sphere, and let's say we want to find out the cut locus of the equator. Recall that the geodesics of spheres are great circles. So if we shoot a geodesic from any point of the equator and try to see which is the first point where this geodesic fails its distance minimal property, then if I shoot it, then till in this direction till the north pole, the geodesic preserves the distance minimal property, and soon I crosses the north pole, I can achieve the same point from the other way, which does not preserve the length after the, which does not preserve the distance minimal property after the north pole, and hence this N is a cut point. And similarly, the south pole will also be a cut point, and hence the north pole and the south pole is the cut locus of the equator. Okay. So note that here this N is a cut point, and it can be joined by at least two minimal geodesic, namely from this side and from this side. And we call this type of point as separating set. So if N be a subset of Riemannian manifold, then separating set, which we denote by SE, it consists of point Q such that at least two distance minimal geodesic from N to Q exist. And we prove that for a complete Riemannian manifold M. So why we are taking complete? To ensure that the extension of any geodesic exists. So for complete Riemannian manifold M and a compact submanifold, the cut locus is the closure of SEN. Okay. So now we will be discussing an example, and with that example, I'll list out some results. So consider the set of all n cross n matrices as a manifold, and submanifold be the set of all n cross n orthogonal matrices. So I can give the Euclidean metric on M and R by identifying the space with Rn square. And this induces the distance between any two metrics A and B as this. So we define F from M and R to R as the square of the distance from the orthogonal matrices. And now let's see what are the properties of this function. So one can show that this function can be explicitly written as n plus trace of A transpose A minus 2 times trace of square root A transpose A. And while expressing this, one can also observe that if A is non-invertible, then this distance can be achieved by more than one matrices. And this function is differentiable if and only if A is invertible. And it is a Morse-Bott function with critical submanifold as ONR. And if I take the gamma t as an integral curve of the minus gradient, then it satisfies this differential equation. And then I can solve the differential equation to get the curve gamma. And now observe that this gamma deforms GLNR to ONR in infinite time. So I should make a remark here that I also have a deformation of GLNR to ONR via the Gram-Schmidt, but that deformation is not geometric in the sense that is like what we do in the Gram-Schmidt. I fix a vector, and the second vector depends on the first vector, and the third vector depends on the last two vectors, and this process continues. But here, this deformation arises from the distance square, and it's more geometric. And one can, and since in the first point I remarked that this distance is achieved by more than one matrices if and only if A is non-invertible, and which proves that the separating set of ONR is the set of all singular matrices. And set of all singular matrices is a closed set, and hence its closure will be itself, and therefore the cut locus of ONR will be the set of all singular matrices. So we will generalize the things from this as theorems. So the first result says that if you are in a connected Riemannian, complete Riemannian manifold, and n be any embedded submanifold of M, and if there are two n geodesic joining the submanifold to a point Q, then the distance square function does not have a directional derivative at Q, and in which direction? So in those directions where like we have two minimal geodesics, and that was happened in the last slide where we saw that the function is not differentiable on the non-invertible matrices. Next, again complete Riemannian manifold and n compact submanifold, then n is a deformation retract of M minus cut locus, and this deformation is via the distance square flow, and here we need that's a Morse-Bott flow. And lastly, the cut locus is a strong deformation retract of M minus n, and in particular this is a good pair, and the number of path components of the cut locus is same as the M minus n. So let us see an outline of the proof of the second deformation. So for that, I'll define a map from the unit normal bundle to 0 infinity as the supremum of the time t, such that gamma is an n geodesic. And the map S is continuous, and it is finite if M is compact. So this continuity is not a trivial fact. For showing that continuity, one needs something called focal points and conjugate points. And so the note that the cut locus is nothing but the image of the SV times V under the normal exponential, where the normal exponential is defined as this. And now I consider an open neighborhood of the 0 section of the normal bundle, and we note that the exponential is diffeomorphic on this U0M, and call that image as UM, which is nothing but M minus the cut locus. So you have this U0M and M minus the cut locus, and if I take a point here, this exponential was diffeomorphism, so I can take this point here, and this deforms to the 0 section. So I have a point here, and then again by the exponential I can go here, and this proves the deformation. So if H is this deformation, then via this diagram one can show that M minus the cut locus deforms to N. Okay, so this completes the first part of the section. So now coming to the topological aspects of the cut locus. So before I'll defining the Thom space. So recall that if pi is a real vector bundle over a paracompact space B, and D with a unit disk bundle and SE with a unit sphere bundle, then Thom space is defined as the quotient of D mod S. And just for a remark, if B is compact, then the Thom space is 1-point compactification of E. So now what is the relation between the Thom space and the cut locus? So for that, we define the re-scaled exponential, which is defined from the unit disk bundle to M. And if I take any point P and any vector V, then I define the re-scaled exponential as the exponential, the Riemannian exponential at S V hat times V if V is non-zero, and if V is 0, then this is P. So note that S is continuous. This implies that this exponential tilde or re-scaled exponential is also continuous, And due to this fact, this is surjective. And the image of exponential, this rescaled exponential, image of S nu under this map is nothing but the cut locus because of the first fact. Okay. So we prove that if N is an embedded submanifold inside a closed connected Riemannian manifold M, and if nu denotes the normal bundle of N, then there is a homeomorphism from the Thom space of the normal bundle to the M mod cut locus. And this leads us some homological results, as we have an inclusion map from the cut locus to M, which induces a long adject sequence in cut locus M and the pair M, cut locus. Now, we observed that this was a good pair, and hence I can change this by the reduced homology of M mod cum. And from the last theorem, we know that the quotient M and the cut locus, it's same as the Thom space, and therefore we have a long adject sequence in the cut locus of N, M, and the Thom space. We also have that if N is a closed submanifold of M with L many components and the dimension of M is D, then the D minus 1th cohomology of the cut locus is free abelian of rank L minus 1, and we have a duality kind of thing that the D minus jth homology of the cut locus is same as the jth homology, a cohomology of M. So yeah, here is typos. And if N is a smooth homology K-sphere, so by homology K-sphere I mean that it's the homology of N is same as the usual sphere. Embedded in a smooth Riemannian manifold, then if the dimension is at least K plus 3, then the cut locus is homotopy equivalent to the D minus K minus 1 sphere. And this ends my talk.
Okay, thank you. Are there questions for the speaker?
How do you prove the duality result?
Sorry?
How do you prove the result about the duality? This H D minus J of the cut locus is the same as H.
In order to prove this, we use the Poincare duality.
Okay, I see.
Are there other questions? Again, if you want to ask a question, just unmute yourself and go ahead. I guess not. Okay, we want to thank the speaker.